Welcome back to the GMP and Quality Fundamentals series, and this is Lecture 22. In Lecture 16, we covered quality KPIs for laboratories. Today, we look at quality metrics from the other side of the facility: the manufacturing environment, the production floor. The lab tracks analytical performance. Manufacturing tracks something fundamentally different. It tracks process stability, process consistency, whether every batch is being produced under the same controlled conditions that were established during validation. This lecture teaches you the metrics that answer that question. Here is what we will cover today. Number 1, you will understand how manufacturing quality metrics differ from laboratory metrics and why that distinction matters. Number 2, you will master the 4 core batch-level KPIs: batch write first time, process yield, reject rate, and rework rate. Number 3, you will learn 4 process-level metrics: line clearance compliance, in-process control adherence, overall equipment effectiveness, and manufacturing cycle time. Number 4, you will understand how statistical process control is used on the production floor to detect problems before they cause failures. Number 5, you will see how these metrics feed the wider quality system through CAPA, Annual Product Review, and Management Review. Let me start by clarifying the fundamental difference between laboratory metrics and manufacturing metrics, because conflating them is a common source of confusion. In Lecture 16 we asked, is our testing reliable? Our OS rate tells us how often results fail. Our right first time rate tells us how often we get a correct result on the first attempt. These are metrics about the measurement process. Manufacturing metrics ask a completely different question. Is our production process in control? Is every batch produced the same way, under the same conditions, producing the same quality output? Laboratory metrics diagnose the analytical system. Manufacturing metrics diagnose the production system. Both are necessary. Neither replaces the other. The metrics that matter in a manufacturing context are batch-level outputs like how many batches are released without problems, and process-level inputs like whether critical in-process checks are being completed as specified. We will cover both categories in this lecture. Let us begin with the batch-level metrics. These are the numbers that tell you what happened to each batch from the moment it was started until the moment it was released or rejected. The 4 core batch-level production KPIs. The first and most powerful is batch write first time, or BRFT. The formula is batches released without any deviation, rework, or out of specification result, divided by total batches started, multiplied by 100. The industry benchmark for an established, well-validated process is above 95%. A BRFT consistently below 90% is a serious signal that requires formal investigation and CAPA. BRFT is the single most powerful production quality metric because it is unforgiving. A batch that required a critical deviation to be investigated before release, or that needed a reprocessing step not in the original batch record, is not right first time. It captures everything that went wrong during production in a single number. One important analytical insight: if your BRFT drops on one production line but not another, the problem is likely specific to that line. Equipment, operator, or environmental conditions. If BRFT drops across all lines simultaneously, the problem is systemic. Raw material, formulation, or process design. The second metric is process yield. The formula is actual output divided by theoretical output, multiplied by 100. The target is product-specific and based on your validated process baseline. A yield of 97% might be excellent for one product and a serious deviation for another. The critical regulatory point here is this: significant yield deviations must be investigated even if the batch passes its specification. An unresolved yield discrepancy means material is unaccounted for. That is a GMP violation. Where did the missing material go? If you cannot answer that question, you cannot release the batch. The third metric is batch reject rate. Batches rejected divided by total batches produced, multiplied by 100. Target is below 1% for mature processes. Above 3% requires formal investigation and CAPA. Analyze rejection reasons carefully. If you are rejecting batches for the same failure mode that had an open CAPA from a previous batch, That is a systemic CAPA failure. The corrective action did not work. Escalate immediately to senior management. The fourth metric is rework and reprocess rate. Rework is when a batch requires additional processing steps beyond those in the original batch record in order to meet specification. Every rework event is a deviation. Every rework event requires a documented risk assessment of the impact on product quality. And every rework event requires QA approval before the batch can be re-released. If the same step on the same product repeatedly requires rework, that is a clear signal that the validated process cannot reliably achieve specification under real production conditions. That is a process validation gap. Now the process level metrics. These are the numbers that reveal what happens inside the production process during each batch. 4 key process level metrics. Line clearance compliance rate. The formula is clearances completed per SOP divided by total clearances required, multiplied by 100. The target is 100%. Anything below 100% must be investigated. Line clearance is the documented verification step completed before every new batch begins, confirming that the production area and equipment are free of any materials, labels, documentation, or other items from the previous batch. A missed or incomplete line clearance creates a direct risk of batch mix-up or cross-contamination. This is one of the fastest routes to a product recall. A note for inspectors. Signed but incomplete line clearance records are more serious than a completely missed clearance. A signed but incomplete document suggests falsification. Inspectors pay very close attention to line clearance documentation. In-process control adherence rate. The formula is IPC checks completed as specified divided by total required checks, multiplied by 100. Target is 100%. In-process controls are checks performed during manufacturing to verify that the process is running within validated parameters at critical steps. Weight checks during tablet compression. pH monitoring during fermentation. Temperature checks during pasteurization. Viscosity measurements during mixing. Each of these checks is defined in the batch record because it is critical. Skipping one means you have a gap in your real-time process evidence for that batch. A critical data integrity point. IPC results should be recorded at the exact time they are performed. If a batch record shows all 12 in-process checks recorded within a 10-minute window at the end of the manufacturing day, that is a data integrity flag. Investigators will look for this pattern. Overall equipment effectiveness, or OEE. The formula is availability multiplied by performance multiplied by quality, expressed as a percentage. World-class OEE is considered to be above 85%. Below 60% indicates significant process or equipment issues. Availability is the percentage of scheduled production time during which the equipment is actually available to run. Performance is how fast the equipment is running compared to its theoretical maximum speed. Quality is the proportion of output that meets specification on the first pass. OEE connects equipment health directly to product quality. A filler with dropping OEE often predicts yield losses and quality failures before they appear in batch records. It is a leading indicator of problems that will eventually appear in your lagging metrics. Manufacturing cycle time tracks how long it takes from batch start to batch release. When cycle times increase significantly, investigate where the time is being lost. Is it in production? In QC testing? In QA review and release? Each bottleneck has a different root cause and a different solution. Chronic cycle time overruns also create organizational pressure to cut quality corners under schedule pressure. That pressure must be actively managed. Statistical process control, or SPC, is one of the most powerful tools available for production quality management. Let me explain why and how it works. The fundamental idea behind SPC is simple. Every process has natural variation. Your tablet weight will not be exactly 500 milligrams on every single tablet. It will fluctuate around 500 milligrams within a range that your validation established as normal. SPC uses control charts to track these measurements over time. The control chart has 4 key reference lines. The center line is the process mean. The upper and lower warning limits are set at 2 standard deviations from the mean. and the upper and lower control limits are set at 3 standard deviations from the mean. As long as your measurements fall randomly within the control limits, your process is in a state of statistical control. But certain patterns in the data tell you that something has changed, even before any single measurement goes outside the control limits. There are 4 key SPC rules you need to know. Rule 1. 1 point beyond a control limit. This is an immediate signal for investigation. Something has caused the process to step outside its normal range. A raw material lot change, an equipment calibration issue, an operator error. Rule 2. 7 consecutive points on the same side of the mean. Even if all 7 points are within the control limits, this pattern has a very low probability of occurring by chance. The process mean has shifted. Something has changed. Investigate. Rule 3. 6 points in a row trending in the same direction. Process drift. The process is moving steadily away from the center. Act before the trend reaches the warning or control limit. Rule 4. 2 out of 3 consecutive points beyond the warning limit. High statistical probability of a real process change. Investigate and take preventive action. The power of SPC is captured in the control chart on this slide. The early data points are stable around the center line. Then a gradual downward trend begins. Points begin approaching and then entering the warning zone. An SPC-trained analyst detects this trend long before any point crosses the control limit. The investigation happens proactively. The correction is made. And the batch that would have failed specification is saved. That is the difference between reactive quality management and proactive quality management. Let me show you what all of these metrics look like together in a real monthly manufacturing quality dashboard. Reading this dashboard line by line. Batch right first time is 97.2% against a target of above 95%. Green status. Stable trend. No action needed this month. Process yield for product A is 98.1% against a minimum of 97%. Green. Stable. Batch reject rate is 0.8% against a target of below 1%. Green, but the upward arrow means this needs to be watched. It is still within target but trending in the wrong direction. Rework rate is 3.4% against a target of below 2%. Red status. This is a significant miss. A CAPA is required this month. The investigation should identify which product, which step, and which root cause is driving the excessive rework. Line clearance compliance is 98.8% against a target of 100%. Amber. Any missed line clearance needs to be reviewed individually. Were they documented as exceptions? Was QA notified? IPC adherence rate is 100%. Green. Stable. OEE on line 3 filler is 71% against a target above 80%. Red. This means the filler is running poorly in terms of availability, speed, or quality. A maintenance review is required. This metric will likely be connected to yield losses if the investigation goes deep enough. Average batch cycle time is 6.2 days against a target of fewer than 5 days. Amber. A QC bottleneck analysis is indicated. Is the delay coming from testing? From review? From scheduling? This dashboard tells a management team exactly where to focus this month. 2 red metrics with clear actions assigned. 2 amber metrics that need investigation. The rest are stable and being monitored. Manufacturing metrics only have value if they are connected to action. And those actions must feed into the wider quality system. The CAPA system is the first connection. Any metric that consistently misses its target must generate a formal CAPA. The root cause investigation must address the reason the metric is failing, not just the individual events that pulled it off target. And after implementation, you verify CAPA effectiveness by checking whether the metric returns to target. The annual product quality review is the second connection. Both EU GMP and FDA require an annual review of each product. Manufacturing metrics are a mandatory input. Batch rejection rates, rework trends, yield trends, and deviation frequency are all assessed over the full year. Regulators check specifically whether trends are being analyzed and whether management is acting on them. Management review is the third connection. Monthly manufacturing dashboards are presented to senior leaders. The review must be formal, documented, and result in decisions. Which metrics need CAPA? Which need resource allocation? Which are being escalated? The decisions made in these review meetings must be recorded in the minutes. Process validation is the fourth connection. If SPC data shows a persistent drift in a critical parameter, or if rework rates reveal that the validated process cannot reliably achieve specification under real conditions, a revalidation assessment is required. This goes through change control and the data is documented, and regulatory submissions connect here too. When applying for product approvals or post-approval changes, manufacturing metrics demonstrate process consistency to regulators. A history of strong BRFT, stable yield, and controlled OEE is evidence that the process is in control. Poor metric history can delay approvals or trigger additional scrutiny from the regulatory authority. Let me finish with the most common mistakes I see in manufacturing quality metric programs. The first mistake is tracking metrics but never acting when targets are missed. A metric with no response loop provides no quality value. Every missed target must have a documented response. Who investigated? What was the root cause? What is the CAPA? And what is the timeline? The second mistake is investigating individual events rather than metric trends. A single rework event is a deviation. 3 consecutive rework events on the same step is a trend that requires a completely different level of investigation and organizational response. Learn to read the pattern, not just a single data point. The third mistake is setting targets without baseline data. Targets must be set based on your historical validated process performance. Arbitrary targets that are unachievable create pressure for data manipulation and selective reporting. The fourth mistake is presenting metrics to management without context. A BRFT of 94% means nothing on its own. Is this better or worse than last month? Better or worse than the same month last year? Better or worse than the validated process baseline? Always present trends and benchmarks alongside the current number. And the fifth mistake, which is a critical GMP violation, is treating yield discrepancies as expected process variation without investigation. Any significant yield discrepancy must be formally investigated. The investigation must determine where the missing material went. If you cannot account for the discrepancy, you cannot release the batch. Let us bring it all together. 6 things to remember from this lecture. Number 1. Manufacturing metrics answer a different question from laboratory metrics. Not is our testing reliable, but is our process in control? Both questions are important. Neither can be answered by the other's metrics. Number 2. The 4 core batch metrics are batch write first time, process yield, batch reject rate, and rework rate. Each has a formula, a benchmark target, and a specific action trigger. Number 3. The 4 core process metrics are line clearance compliance, IPC adherence, OEE, and cycle time. These metrics reveal process health in real time, during production, before failures appear in final batch results. Number 4. Statistical process control detects trends and shifts before any single measurement fails specification. 7 consecutive points on one side of the mean is a signal, even if all are within control limits. Act on the trend, not the failure. Number 5. Manufacturing metrics must be connected to CAPA, annual product review, and management review. A metric with no action loop provides no quality value. Number 6. Every yield discrepancy must be investigated. Unaccounted material is a GMP violation. This principle has no exceptions. That is Lecture 22 complete. And we are one lecture away from finishing Level 2. Coming next in Lecture 23, the final lecture of Level 2, we cover laboratory investigation best practices. How do you investigate a laboratory failure properly? What is the difference between a Phase 1 and a Phase 2 OS investigation? How do you structure the investigation? What evidence do you gather? And how do you write a conclusion that holds up under regulatory scrutiny? After Lecture 23, Level 2 is complete. And then Level 3 begins. Chromatography fundamentals. HPLC, GC, and the analytical methods that sit behind GMP testing in laboratories around the world. If this lecture helped you, please give it a like. Subscribe if you have not already. And leave your questions in the comments below. I reply to everyone. I will see you in Lecture 23.